Yes, so in the previous video, we're actually looking at a very curious phenomenon. Okay, we said that over a family of rotating equilaterals, the blue ones, if you actually affix a point P to the circumcircle, and now you consider the derived family of cevians with respect to P, one thing that we did notice was that the locus of the body center of these cevians is a straight line. And the straight line happens to be perpendicular to the line connecting the center, let's call the center O and P. So if I drew a perpendicular here, if I actually drew the line OP, I would notice that this locus is perpendicular. Okay, so what I want to do today is actually say, okay, what happens if I now apply an affine transformation to the system? And now I have the so-called Poncelet homothetic family. So this is a family of triangles interscribed between two homothetic concentric ellipses. And I want to know if this alters in any way the phenomenon that we saw in the previous video. So we know that the body center of a triangle is projectively invariant, and the cevian is also projectively invariant. So we expect that this affine transformation, though it's going to change the angle, okay, that this line here is, say, with respect to line OP, everything here is projectively invariant. In fact, the body center is the only triangle center which is projectively invariant, so it should be affinely invariant. So we continue to have the phenomenon that over this now Poncelet family, which is an affine image of the equilaterals, the locus of x2 continues to be a straight line. So we need to just prove this phenomenon for the equilateral case. How about x3? And I'm going to do it in this following way. I'm going to go back to the equilateral first, and then I'm going to say, okay, let's take a look at x3. x3 was a set of, the locus of x3 was a straight line previously. Not obvious at all why this is the case. Okay. Again, it's a straight line perpendicular to the OP line. By the way, this is obvious if you consider that, or let's say this is a corollary of the fact that x4 was a stationary point at the center. Okay, but let's just look at x3 independently of x4, because I want to look at the affine. So when I now apply an affine transformation, x3 is no longer a straight line, and the system here is saying that this is not even a conic. So if you look at this curve from afar, you can see that there's some curvature here that changes sign. So x3 ceases to be a simple curve. This is, you should not trust what's up here, because my conic detector, when things are super stretchy, sometimes is not very reliable. And this is a very stretchy, likely infinite curve, which clearly is non-conic, because you can see here this sort of sinusoidal shape to it. Okay, now the reason this can no longer obey what was a corollary of x4 being stationary is because x4 itself is actually doing something non-trivial. So let's go back to x4. Remember that it was nicely stationary over the equilateral family, but as soon as I move away 1 iota from this and I apply 1 iota of affine transformation, x4 in a way explodes. Okay, so x4 now becomes, as I start applying my affine transformation, a non-conic. So there's a sort of transition from something that looks pretty close. So it's almost as if the limit of this thing is a shrinking locus, right? So it's a shrinking finite non-collinear locus, non-linear locus, non-conic locus, that as I move closer and closer to the equilateral case, so this is starting to look like a straight line segment, the length of the segment is shrinking to nothing, and if I keep cutting this in half, you can see here that at some point I get to something that I'm having some numerical instability here. When I get to 1, this thing just sort of suddenly jumps to a circle. So corollary that this guy is stationary and x2 is a straight line for the equilateral case, as we said before, is the fact that the locus of x3 is linear in the case of the equilateral. Now if you apply the affine, we saw that x2 remains a straight line given the projective argument. However, x4, which was helping us with the corollary on x3, is no longer a point. So what ends up happening is that x3 in its turn is no longer a conic, not even a conic, because x4 is not a conic. So if you think of the fixed linear combination on the Euler line that x3 is of x4 and x2, since x4 is not a conic and x2 is a straight line, you don't expect x3 to be a conic, and it is not. Okay, so you should ignore this up here. This is, yeah, so this in general is not a conic. Okay, how about x5? I think by the same token, it's not going to be a conic because, again, Euler line, fixed linear combination of x4 and x2, so not a conic. How about x6, which we had previously associated with a very neat, what I called inherent ellipse, where one of the minor semi-axes of this inherent ellipse was actually the circumradius divided by 10. Okay, what happens to x6 as I apply my affine transformation? Let's take a look. Now x6 is becoming something that is obviously not a conic, so not interesting. And I can go through other other triangle centers which were non-conics even in the equilateral case, such as the Gergon, or this would be the Nagel point, which is out there. How about the Mittelpunkt? Mittelpunkt looks pretty straight, right? But it's not being detected as being even a conic. How about the Speaker center? Not a conic. How about the Feuerbach point? Also not a conic. I can play. Feuerbach point tends to be quite artistic in general. So we can see here that in this case it's generating this sort of teardrop-shaped object. As I move P around, oh, we can have self-intersections. Oh, that's quite nice. Let's put it over here. Let's increase the sampling further, and let's move A a bit to see what happens. Yeah, so we can see here that X11 is quite an interesting character. You can have self-intersections, and this is a pretty high degree curve in general. So, okay, so we can go through X12, which is this beanie shape thing, not interesting. But then we go back to X13, and what I'm going to do is I'm going to go back to, so we remember what X13 was doing in the case of the equilaterals, right? So let's recenter this family, and let's just look at X13 here. And remember that as we move the equilaterals around, X13 was stationary at P. So let's now apply the affine transformation. Look at what happens. Pretty quickly, X13 becomes a nondescript oval. Okay? Is it even symmetric about an axis? We don't know. When I see more complicated objects like this, I often don't analyze them right away. How about X14? What was X14 previously? X14 was a circle tangent to the circumcircle of my equilaterals at P and of the same radius. What happens if I apply the affine? Again, I lose circularity, I lose conicity, so this thing is some nondescript curve. Same thing for X15, now it's an oval. And there's one thing that might be interesting here, is that over P, let's see if this is true. Yeah, the oval of X15 seems to have a preference to be somehow upright. Okay, it's not even always tangent to my outer ellipse. Remember that the sky was a circle in the case of the equilaterals, and now it's become this nondescript thing. X16 should have the same kind of behavior. Remember that X16 was a circle, perfectly tangent to my circumcircle at P, and containing the circumcircle. And now when I apply the affine, I lose this harmony. So looks like the only thing that sort of kept its property post-affine for this particular case was X2. Go back to X2. Because of its affine invariance, both cevian and the X2 being affinely invariant, since and actually projectively invariant, we are retaining the property that X2 remains a line over this homothetic Poncelet family. Okay, in the next video I'm going to explore another dimension that we can explore, which is what happens to these loci when my point P is not necessarily in the outer conic of Poncelet or the outer circle of equilaterals. I can actually move it around. In fact, I'm going to start analyzing this when P is on the inner, on the in circle in the equilateral case, or in the caustic on the sponsolation case. So I'll see you in the next video.